Hello and welcome to week 8's discussion on the course of electric circuits. So today we will be discussing a very important concept of how to find out time constants for circuits that have only single energy storing element. So the question that we are going to address today is how to find out time constants for circuits having a single energy storing element. This is the question. So let's take an example. So let us say we have this circuit. These are the load terminals. Let's say we name them A and B. Here we have capacitor, only single energy storing element, and we have two resistors R1 and R2. This is C. So that how to find out the time constant without using Laplace expressions or anything. So it's very easy. So what we need to do is we need this AB is this I said load terminal. This is the source terminal actually. So here we can add a source. Let's say a voltage source is there. Now to find out the time constant for circuits having single energy storage element, what you need to do is consider you have the energy storing element C. So you just take these two terminals and remove it from the circuit. So the circuit becomes R1. Here is the voltage source plus minus V, and here is the resistance R2. This plus minus terminal, and here the capacitor was connected. We have removed that capacitor, right? So next is, so the first rule is remove the energy storing element. Second is consider the Thevenin resistance across the terminals of the energy storing element. So we have to now consider the Thevenin resistance across the terminals of the energy storage element. This is this plus and minus sign. So what is the Thevenin resistance here? So here R Thevenin. So to find out Thevenin resistance, we need to short the voltage sources and open the current sources. So here it will be shorted. So we have R1 parallel to R2, so that is equal to R1 R2 by R1 plus R2. So this is R Thevenin. Now hence we can say the time constant tau, which is the time constant which we want to find. So time constant equals R Thevenin into C, that is equals to R1 R2 by R1 plus R2 into C. So this way we can find out the time constant for circuits having a single energy storage element. Here we have a capacitor. You can also show the same thing for an inductor as well. So the rules are: to remove the energy storage element, consider the Thevenin resistance across the terminals of the energy storage element. So you will get RTH, and accordingly you can find out time constant to be RTH, it's the Thevenin resistance into the capacitance. Let's now take an example with inductor as well. So say we have a current source R1 R2 and inductor, that is L. Now this is I. So the first rule is to remove the energy storage element. So let's remove it. So removing the energy storage element, we have R1, this is open, this is open. Here we have oh sorry, this is R2, this is R1, and we have a current source here. So we need to consider Thevenin resistance across the terminals. So across the open terminals we need to consider the Thevenin resistance. So here it's a current source, so it will also remain open. Hence RTH equals R1 plus R2. Hence tau, that is the time constant, equals to, what is the time constant in case of inductor and resistances? It's simply L by R, that is equal RTH. So it's L divided by L divided by RT. RTH is R1 plus R2, so it is R1 plus R2, the time constant. So like this we can find out the time constant for single energy storage element circuits without even doing the Laplace transforms. Next we will be doing the problems of assignment 7, and you can check your answers whether you have done it correctly or not. Or if you have any doubt in assignment 7, you can get it clarified once we do the problems. So let's start. So the number 1 problem is: the switch has been in position 1 for a long time and abruptly changes to position 2 at t equals to 0. Okay, so switch was like this at 1 for a very long time, and it abruptly changes to 2 at t equals to 0. So if time t is in seconds, the capacitor voltage Vc for t greater than 0 is given by. Okay, so let's do this problem. So let's copy this circuit. So when it is connected to 1, capacitor under steady state condition behaves as an open circuit. So the voltage across the capacitor will be basically, so 3 ohm and 2 ohm, so 2 ohm it will be a voltage divider 5, so 4 volt should come across the capacitor, but we will check it. So you have 3 ohms, and here is 10 volt, here is 2 ohms, here we have the capacitor, so it will behave as an open circuit. 0.1 farad I guess, right? So since it is an open circuit, so Vc for 0 minus will be 10 into 2 by 5, so it's equals to 4 volts. Right? Now once the switch is connected to position 2, what will the circuit become? Let's see. 4, 2, 2 and 5 ampere up. So 4 ohms, then we have a 2 ohms resistor. Here also we have a 2 ohms resistor. We have a 5 ampere current upward. Yep. And here we have the capacitor of 0.1 farad and plus minus 4 volts. Right, so let's now write down the equation. Let's consider this to be this direction to be I1, this we know 5 ampere, so this to be, let's say, I2. So you can write the expressions in Laplace domain directly. So what we will have is I1 equals to C, that is 0.1 dVc by dt. So from here we get in Laplace domain I1s is 0.1 S into Vc S minus 4. Right, so this is my one equation. My next equation is I2s is I1s plus 5ys. Second expression. My third expression is the KVL equation in the first loop, that is in this loop. We will be writing the KVL equations. So that is equals to 0.1 integral I1 dt plus still minus infinity t. We shouldn't say t, we can consider this to be tau, and then we have 4 times I1 plus 4 times I2 can be written as 2 times I2, so that means just 2 times I1 plus 10 equals 0. These will, all of them will be negative. So let's solve it. Now let's solve it. So we have, so that taking Laplace domain, we can write it as I1 s by s into 0.1, okay, minus so this is integration of this term. So here, from here we can write it as minus four by s that's the voltage, right? So that's the voltage, plus 6 I1s plus 10 by s equals 0. So I get I1s into 6 plus 1 by s into 0.1 equals to minus 6 by s. Now I can write I1s is equals to minus 6 by 6s plus 10, that is equals to minus 1 by s plus 10 by 6. So that is equals to minus 1, in time domain I can write I1t equals to minus 1 e to the power minus t by 0.6 ampere. So therefore the voltage across the capacitor will be I can do it in Laplace domain only. So VCS equals to, it's I1s by 0.1 S plus. Plus plus minus 4 by s. Oh, there it will be plus. So from here I can write this to be, we have this, so minus 10, let's say, s into s plus 10 by 6 4 by s. So from here I can write minus 10 1 by s minus s plus 10 by 6 put 1, then what will we get? S plus 10 by 6 on this side, s cancels out, so 10 by 6 will be the output. So we have to multiply the outer side with 6 by 10. Okay. So 10 cancels out, and we have minus 4 by s. Now to calculate the value, we have now ten by s minus 6 by s plus 10 by 6. From here we obtain 10 minus 6 e to the power minus t by 0.6. That is our VCT. So hence we have obtained the result. This is option D, I guess. D is the answer. Let's go to the next problem. In the figure shown, the ideal switch has been open for a long time. So this switch has been open for a very long time. If it is closed at t equals to 0, then the magnitude of the current in milliampere through the 4 kilo ohm resistor at t equals 0 plus will be. It is closed at t equals to 0, so it's open for a very long time. So once it's open for a very long time, so we have 10 volt voltage source, 5 kilo ohm, 4 kilo ohm and a 1 kilo ohm. So let's write it down. A 10 volt test source, we have a 5 kilo ohm, 4 kilo ohm and 1 kilo ohm. So Yeah, and a capacitor of 10 microfarad and 1 millihenry. So here we have a capacitance 10 microfarad. Here we have the switch, and here we have 1 millihenry. So if the switch has been open for a very long time, the capacitor will behave as a open circuit and the inductor will behave as a short circuit. Okay, so the voltage across capacitor VC 0 minus is 5 volts, as it's basically a voltage divider. So you have 5 kilo ohms on this side, this is open, so it's 5 kilo ohms on this side as well. And this is short. So the voltage here is 5 volts, and the current through the inductor IL0 minus, so it's short, so what is the current through it? 10 by 10k, that's 1 milliampere. So the answer here will be 1 milliampere. Not the answer, the current through the inductor at time t equals 0 minus. Now at t equals 0, the switch is being closed. So now as the switch is being closed, and at t equals 0 plus, we are expected to find the inductor current, I guess. The current IM, the current through the 4 kilo ohm. Okay. So as we switch it on, the capacitor will now behave as a short circuit. So it can be modeled as 5 kilo ohm. Here we have 10 volts. Here we have the capacitor is being shorted with the 5 volt, and it's 4 kilo ohms, 1 kilo ohm. This is again short, and this side the inductor end, we have a current sink of 1 milliampere. Now we need to find out this current. This current is what we are interested in, I1 at t equals to 0 plus. So this current I1 at t equals to 0 plus is nothing but we need to do the KVL in this loop. So that's 5 volt. We have only one voltage, so that's 5 volts. The voltage captured across the capacitor by the 4 kilo ohm resistance, 4 kilo ohms. This will give us 1.25 milliampere. That's the answer. I think the option is B. Next problem. if the unit step response of a network is 1 minus e to the power minus alpha t, then its unit impulse response is. So it's also again an easy problem. So we have the unit just a second, plus equals 5 by 4 milliamps, that gives us 1.25. Oh sorry, the B answer. So next is the third. We are with the unit step response is 1 minus e to the power minus alpha t, 1 minus e to the power minus alpha t. Find out the unit impulse response. We need to if this is y, since impulse is the derivative of step, impulse response is also the derivative of step response. So y2 is dy by dt, which will give me alpha e to the power minus alpha t. This is the answer. It's option A. Let's do the next problem. So it is asked that in the following figure, C1 and C2 are ideal capacitors. C1 has been charged to 12 volts before the ideal switch S is closed at t equals 0. The current IT for all t is. Let's find out. So C1 is initially charged to 12 volts and C2 is uncharged. So when the switch is closed, the circuit becomes such. This is C1, this is C2, this is the voltage or the charge, it's 12 into C1. So when the switch is closed, there will be a current flow. Let's say it is IT. Taking Laplace transform, I can say IS equals how much? How much will be IS? So to do this problem, we need to see. So what we have is a 12 volt source. So it is the voltage source is 12 by S divided by what's the total capacitance. So we have two capacitors, they are in series, so it's 1 by S C1 C2 by C1 plus C2. So what we obtain is 12 IS equals to 12 C1 C2 by C1 plus C2. If we convert it into time domain IT, it is 12 C1 C2 by C1 plus C2 times delta t. So it's an impulse function, hence the answer is a impulse function D. So D is the answer. And then we have a last problem, that is the condition of RLC such that a step response YT, that's the voltage across the capacitor in figure, has no oscillations. Well, let's see. we have a unit step input L, R and C. We are measuring the voltage across the capacitor, so that capacitor voltage should not have any oscillation. So oscillation, when does oscillation happen? When the characteristic equation of the system has complex conjugate poles. So to avoid oscillations, we should not have a complex conjugate pole. So how to do this kind of problem? So we have inductor R and C. And let's say we have a unit step ut. So we can write in Laplace terms, we can write VCS equals 1 by SC into 1 by S divided by SL plus R plus 1 by SC. So multiplying SC on top and bottom, we get 1 by S square LC plus SCR plus 1. So it's 1 by S square LC plus SCR plus 1. Now let's break it down. So I can write 1 by S minus SL plus R times C by S square LC plus SCR. Sorry. Now to prevent complex conjugate poles, so this is a simple pole at S equals 0, so this won't cause oscillation. So oscillation can occur due to this second order characteristic expression S square LC plus SCR plus 1. So what are the poles? Poles are S equals to minus of RC plus minus root over RC squared minus 4LC by 2LC, right? So I can simplify it R by 2L plus minus root over R by 2L whole square minus 1 by LC. So this term inside the determinant must be always greater than 1. So R by 2L whole square should be greater than equals to 1 by LC. So R square by 4L square should be greater than equals to 1 by LC. Or I can write R square by 4L should be greater than equals to 1 by C. Or R will be greater than equals to 2 root over L by C. So this is the condition. This is option C. option C. So thank you for watching the solutions for assignment 7. Hope this helps you in your examination and help you understand the concepts of electric circuits as well. So thank you.